कल कल रात में टेस्ट किए थे इसको? हाँ। हाँ? ओह, वो गोवा हो गई क्या? अच्छा, ସେଥିପାଇଁ ଆସିଲା ଏଇଟା ଦେଖିନି। ये क्या है देखो।
हेलो ମୁଁ କେମିତି ଜାଣିବି ଯା ଛୋଟ ନେଟ୍ ମୋବାଇଲ देख तो ये ऑडियोटा शुभुच ना ना टे रिफ्रेश कर छाड़ सुन तो जा हेलो 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 आसुची ऑडियो हाँ हेलो हेलो
ଅନଲାଇନ୍ରେ ଆସୁଛି ନା ଆମର ଯେଉଁ ଭିଡ଼ିଓରେ ସାଉଣ୍ଡ ଫିଡ୍ ଆସୁଛି ତ? ऑफिस से ना। ये लगेगा कौन सा बैटरी है ये? डबल है डबल है डबल है। तो वो लेके रख देते हैं। ठीक है, बाकी फीडिंग देख लीजिए, तब तक वो आ जाएगा जो यहाँ पर देखते हैं। जी जी।
ହ୍ୟାଲୋ 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 ନଏସ୍ କିନ୍ତୁ କମିଯିବ ସାର୍ ଏତିକି ଆପଣ
हेलो।
This course is a unique opportunity for us to explore the intersection of network control systems and reinforcement learning, a field that is shaping the future of automation, robotics, and intelligent decision making. Through this program, we will engage in collaborative learning, explore applications relevant to both academia and industry, and gain valuable insights from our esteemed faculty, Professor Jagannathan Sarangapani sir, from Missouri University of Science and Technology, a distinguished expert in the field of network control systems as well as reinforcement learning. We are honored to have you, sir, and we eagerly look forward to an enriching session with you. Without further ado, let us begin. It is said that the most auspicious way to begin any endeavor is by doing Deepa Prajwalan, which symbolizes wisdom and knowledge. Shubham karoti kalyanam Arogyam Dhanasampada Shatru Buddhi Vinashaya Deepa Jyotir Namostute. So I now invite our honorable dignitaries to come forward and mark the inception by lighting the lamps. So please. Our chief guest, Professor Jagannathan Sarangapani sir, Professor Pradeep Sarkar sir, Director in Charge, NIT Rourkela, Professor KB Mohanty sir, HOD, EE Department, Professor SK Sahu sir, Local Coordinator for GIAN NITR, and Manas Bera sir. Thank you, sir. So I now request, please kindly take your seats in the dais, sir. So I request all of you to have your seats here, sir. May I now invite Professor Manas Bera sir, coordinator of this course, to deliver the welcome address. Sir, please.
Respected Professor Jagannathan Sarangapani, distinguished Professor, Missouri University of Science and Technology, and chief guest of this inaugural function, Professor Pradeep Sarkar, Director in Charge, NIT Rourkela, Professor SK Sahu, Local GIAN Coordinator, Professor KB Mohanty, Head of the Department of Electrical Engineering, respected other dignitaries, dear colleagues and participants. On behalf of the Department of Electrical Engineering, NIT Rourkela, we are greatly honored and pleased to welcome you all to the inaugural ceremony of the 10 days GIAN course on network control systems using reinforcement learning. It is a great pleasure for me to welcome the participants from all over the India who came here to learn this particular topic. We are happy to inform you that we have 43 number of registered participants. Amongst them, 8 participants are from outside of NIT Rourkela. And this course is going to be offered by Professor Jagannathan Sarangapani. So let me introduce him formally. He is from Missouri University of Science and Technology, where he is at present Rutledge Emerson Distinguished Professor. He served as the site director for the graduated NSF Industry University Cooperative Research Center on Intelligent Maintenance System over 13 years. He has a joint appointment with the Department of Computer Science and the Department of Engineering Management and System Engineering. Prior to joining the Missouri Science and Technology, he was employed at the University of Texas at San Antonio and Caterpillar Inc. His research interests include adaptive and neural network control systems, cyber physical systems, sensor networks, and autonomous systems and robotics. He has co-authored 163 peer-reviewed journal articles, 277 referred IEEE conference articles, several book chapters, and 6 books. He holds 21 patents with several pending. He so far supervised the completion of 29 doctoral students and 30 MS students. He received research funding from NSF, NASA, AFRL, Sandia, and industries such as Boeing, Caterpillar, Honeywell, and others. He served as the co-editor for the IET book series on control from 2010 to 12, and on a number of IEEE conference organizing committees, including chair of IEEE CSS Tech Committee on Intelligent Control. He is a fellow of IEEE, US National Academy of Inventors, IET UK, and Institute of Measurement and Control UK. He received NSF Career Award in 2000, Caterpillar Research Excellence Award in 2001, Presidential Award for Research Excellence at the University of Texas in 2001, Boeing Pride Achievement Award in 2007, several faculty excellence and teaching excellence award at Missouri Science and Technology, and many others. Sir, I welcome you to the Department of Electrical Engineering, NIT Rourkela. Also, a very warm welcome to all the participants joining us today for this 10 days course. We are thrilled to have you here and excited to embark on this learning journey together. Over the next 10 days, we will delve into different key aspects of network control system, providing you with the valuable insights and practical skills. Please feel free to actively participate, ask questions, and make the most of this opportunity to enhance your knowledge in this area. With this, I thank you and welcome once again.
Thank you so much, sir. Now I would request Professor K.B. Mohanty, sir, Head of the Department of Electrical Engineering, to offer a warm welcome to everyone. Sir, please.
Respected Chief Guest, respected Director in Charge, Coordinator GIAN of NIT Rourkela, and Coordinator of the GIAN course, Professor Bera, other faculty members and dear students present, and all the participants who are participating offline or online. A hearty welcome to the Department of Electrical Engineering and in this GIAN course on network control systems using reinforcement learning. So Department of Electrical Engineering is very old, and it is here in this campus since the beginning from the year 1961, and department has a very good research facility and excellent teaching lineage, and there are several courses conducted, and there are several GIAN courses are also completed here. Professor S. Das started the GIAN course long back, and since then several GIAN courses are conducted in the department, and participant and resource person comes from different parts of the world to enlighten the participants and the students, and that way we are benefited by all the GIAN courses, and I hope all the participants and all the students attending the class course will be benefited by the GIAN course, by the lectures and the lab sessions. I wish a fruitful outcome of this GIAN course. Thanks all.
Thank you, sir. Now, I would request Professor Pradeep Sarkar, sir, Director in charge of NIT Rourkela, to felicitate our chief guest, Professor Jagannathan Sarangapani. If we can have a round of applause. May I now request Professor K.B. Mohanty, sir, HOD of EE Department, to continue the felicitation of our honorary guests to Professor Pradeep Sarkar, sir, Director in charge, NITR. If we can have a round of applause. Now I may call upon S.K. Sahu, sir. Sir, Mohanty, sir. Professor S.K. Sahu, sir, the local coordinator for GIAN at NITR. Now I request Manas Bera, sir, to felicitate Mohanty, sir. Moving ahead, now I request Professor S.K. Sahu, sir, the local coordinator for GIAN NITR, to address our esteemed audience. Sir.
A very good morning to all and welcome to the GIAN course, Network Control Systems Using Reinforcement Learning. Respected Director in Charge, Pradeep Sarkar, the foreign expert of the GIAN course, Professor A.S. Jagannathan, Head of Department of Electrical Engineering, Professor K.B. Mohanty, Course Coordinator, Dr. Manas Kumar Bera, faculty colleagues, participants, students, ladies and gentlemen. GIAN is basically a Sanskrit word which means knowledge. It has an abbreviation, Global Initiative of Academic Network, which is already the announcer has discussed. It's a program of the Ministry of Education, Government of India, designed to tap the talent pool of scientists and entrepreneurs internationally to encourage their engagement with the institutes of higher education in India to augment the country's existing academic resources, accelerate the pace of quality reforms, and elevate India's scientific and technological capacity to global excellence. GIAN enables institutes of higher education in India to invite and host internationally renowned academicians and researchers, facilitating the co-teaching of advanced courses to Indian students and fostering collaborative relationships with experts from around the world. GIAN offers internal experts a unique opportunity to familiarize themselves with India's academic environment. By interacting with the local students and faculty, these experts can explore potential collaborations, share their expertise, and contribute to the advancement of knowledge across diverse fields. Already NIT Raulkela has conducted around 30 courses. In this phase, around 9-10 courses already we have done it. Another 4-5 is to be done in this session. Coming to the subject, so it's basically what I, as a layman, what I understand, like civil engineering, we have a plain concrete and a reinforced concrete. Here also the control systems, network control systems has a reinforcement, either artificial intelligence or machine learning. Here I think they will be discussing a lot on the influence of artificial intelligence on the control systems. So the best thing they can tell you. So all best wishes for the persons involved in making the course a success. Thank you very much.
Thank you so much, sir. Now I'd request our chief guest and the resource person for this course, Professor Jagannathan Sarangpani, to enlighten us with his words of wisdom. Sir, please.
Good morning to all of you. It's a distinct pleasure for me as being here, and wanted to thank the people on the podium, Dr. Sarkar, the director in charge, Dr. Mohanty, the head of the department, Dr. Sahu, the coordinator for the GIAN, faculty who are here, and my dear students. This is my first visit to this part of the country, India. Although most of my brought up has been in the south of India, and the places that I've seen is Lucknow or the Kanpur area and Delhi in the northern side. So it's interesting to, when I've been invited, Professor Bera and I have been in contact when he was in Silchar for a long time. And so Rourkela, I heard only the Steel Authority of India plant. So this is, I have not seen, but it was really nice when I was driving back. Amazing city, very clean compared to a lot of places. So, but it's a pleasure, as I said, come here and discuss this. So GIAN is a good program. There are a lot of different programs through Ministry of Education, and this is a very interesting program. Most of you probably know. It invites a foreign faculty to come and kind of lecture. The good thing about this particular one is that we are trying to do lab component along with the actual lecture, because usually lecture means after the lecture students forget and they go away. So the lab component essentially helps the student to run some of the programs that we built, and it took us a little time because of the versions, different versions, as you probably know. And finally, I think it's supposed to run on some of the machines. So, and AI, this is an era of AI, and what we call cyber physical systems. It's not actually driven by, you'll be surprised, a lot of us think it's driven by the computer science people. Unlike computer science, it's driven by the engineering people, mainly because it's a real-time study, right? So most of the AI you heard from Google or anybody, they talk about mostly offline data, training and all that. Most of the real-time control or any other engineering field, it's much more serious. Imagine you have a nuclear plant, you're adding AI, it has to meet so many different constraints than just you applying it to an offline, science side. So it's you should be proud. If you're an engineer, it's a lot harder to do than if you're a computer scientist. At most, if things hang up, you just go and press the power button. But that's not that easy if you are looking at a engineering field, especially control. Things can blow up, as most of you know. So nobody talks about it. But it is very critical aspect in there. So this course, I think Vera and I have been looking at it. I know he has PhD students who worked with me. So I think it would be an interesting one. And as I said, it so happened, we were just discussing that the approval came a bit late, I guess, that this is why we have to schedule it now. I know there were a few others that wanted us to do it in the summer or when there are colleges closed, or on vacation. But in any case, it's a pleasure to see you, most of you. I hope to see you in the course. Thank you very much.
Thank you, sir. We hope you have a warm stay here. Now, I request Professor Pradeep Sarkar, Director in Charge, NITR, to share his valuable thoughts on this occasion.
Esteemed Chief Guest, Professor Sarangapani, my colleague, Professor Mohanty, Professor Sahu, Professor Bera, and other professors sitting off the dais, students and participants, very good morning to all of you. And on behalf of the Institute, I welcome you to the inaugural program of this GIAN course. The GIAN course, this course is being conducted under this GIAN program, Ministry of Education's one very prestigious program. And GIAN is not only a knowledge transfer, but it is aimed to empower the future workforce of our country. And as you know, our country is going through a transformation in our education policies. We are moving towards the more holistic education system with focus on important aspects like skill development and institute-industry relationship, things like that. So NEP 2020 has already set the foundation for this transformation. And the course that that is going to be discussed in 10 or 15 days time, 10 days time, is on network control system with reinforcement learning. As I am also from civil engineering, we think reinforcement means only steel reinforcement. But although we are not expert in this subject, but one thing we know is that there are a lot of possibilities ahead in this subject. And this subject is actually talks about the skill development, this course, and institute-industry relationship. So another very interesting, we are really privileged to have Professor Sarangapani here. And in my brief interaction, I understood he is not only an expert, distinguished expert in the field, who is there in University of Missouri Rolla, name is changed now, but he has also large experience in the industry. So he brings here a rare combination of industry as well as academia. And on behalf of the Institute, I really appreciate, sir, for your time and effort that you are spending for us. So for the participants and students, I request that this type of opportunity you are not going to get every time. It is not other lectures we generally have in our department. Will not regularly get a people like Professor Sarangapani. So you take advantage of this time, his presence, and we are looking ahead, the country is looking ahead for becoming a developed nation by 2047, Viksit Bharat, and we want skilled manpower, and all these initiatives of Government of India is with a objective to develop the skill of our youth. So only because if you engage yourself in programs like this and think about entrepreneurship, skill development, there are ample opportunity in this particular subject. So then only we can achieve our objective to become a developed nation by the 100 year of our independence. So I am very happy and proud of some of our colleagues who are taking initiatives to organize this program for the benefit of the people, our students and the youths of India. I wish this course be a very successful one, and this course add value to your understanding. Already you have some understanding in this subject. I am sure this is going to add more value to it. Thank you very much.
Thank you so much, sir. As we come to the end of this enriching inaugural session, I now invite Professor Manas Bera, sir, to extend the vote of thanks and express our gratitude to all those who made this event possible. Sir, please.
Thank you is such a prayer that cannot be seen or touched. It must be felt by heart. I feel honored and privileged to get the opportunity to propose the vote of thanks on this special occasion. I would like to thank all the participants for their presence. I am also very much thankful to Professor Jagannathan Sarangapani. The key person of this course has agreed to visit NIT Rourkela and agreed to taught this course. Words are not enough to thank him. And I, on behalf of coordinator, I convey deep regards and hearty thanks to our Honorable Director, Professor K. Uma Maheshwar Rao. I am also thankful to the Registrar, Professor Rohan Dhiman, Professor S.K. Pratihar, Dean SR, and Local GIAN Coordinator, Professor S.K. Sahu, Head of the Department, Professor K.B. Mohanty, Dean PND, Professor Sarkar. They helped us in obtaining the necessary administrative approval for the organizing this event in our campus. They supported in all possible manner to organize this GIAN course. I am very much thankful to all our faculty colleagues and non-teaching staff members who always stand by us and motivate us. I feel proud and thank you for making this event a successful one. An event of this dimension cannot happen in overnight. We have been fortunate enough to be backed by a team of very motivated and dedicated student volunteers. I am very much thankful to the Ministry of Education, Government of India and IIT Hyderabad, GIAN Coordinating Institute for financial support. It would have been impossible to organize it without their support. I would also like to thank our transportation, accommodation and catering team. Without you guys, the event was not possible to make. Thank you very much again. And for outside participants, have a wonderful stay at NIT Rourkela. Enjoy this GIAN course and the campus life of NIT Rourkela. Thank you. Okay, now we are going to end this program, and thing is that the high tea will be little bit late. So in between, what we will do, we will take a group photo. So please, we will join for the group photo. Okay. Thank you all the participants, faculty members, and dignitaries. Thank you. This is actually made of tussar. It is called tussar. ये very handcrafted resin. I think this is what the
Excellent. All right, guys. Good morning. Still, we still have an hour before it becomes afternoon. So, thank you for introducing yourself. Let me say myself. I'm a faculty in Missouri Rolla. It's now called the Missouri University of Science and Technology. And thanks for joining this class. I was just telling a few people that today's lecture would be more like giving you like what is going on and what's going to happen in the next 30-40 years. So we will do a little bit intro today, and I wanted to, since I don't know how many of you have background in machine learning or reinforcement learning, so I'm going to give you a little bit background very fast. You're going to see this because there are multiple courses you have to take if you really have to go one at a time. So imagine I'm kind of putting everything together in a fraction of less than 2 weeks. Okay, so and about 20 lectures, that's not possible because each of those courses are a full-fledged semester level courses. So, and this is at the highest level for PhD students. So that's number one. Number two, I was just saying don't miss any labs. Okay, I hope that there is somebody to help us to run those, because the programs you could run them even if I'm not here. Okay, so make sure the most important thing is make sure you get a copy of this book. This was published in 2016. Okay, this comes with the MATLAB code, and the only thing is, as part of this course, we are offering the code. That code was basically converted to the most recent MATLAB version, which is 2023. So it should run, and it's pretty good. So the good thing with that is you remove the system dynamics, and replace it with any system. It should work, either aerospace system or anything. You don't need the dynamics for the controller. That's the basic benefit of it. Okay, so everything is taken from this book. It's a public knowledge. There is this came out of research, and you see that there is a second author. Was the guy who did this? He's a former PhD student. Typically, that's what happens, and they become a faculty, right? Like you guys. So he's a faculty in US right now, and so this was published in 2016. So get a copy. This is very important. What goes on? Okay. So with that short intro, and I'm here, so if you have questions or something, you guys can ask me. So I was also telling a few people here, if there are PhD interested students to pursue in the US, please let me know. I think there will be an email I'm going to show you. Okay, so this network control systems is a specific topic, okay, of what we call cyber physical systems. How many of you have heard of cyber physical systems? Yeah, so the cyber physical systems, the word has been coined in 2006. 2006 is what it is. So every system that you see currently being operated, we call that as cyber physical. So the reason it's called cyber physical is because you have a physical system like a batch reactor or a plane or some kind of a gear system, a battery system. That's a physical system. Then you have some sort of a controller, or what we call is a embedded processor. So you have a cyber, you have a physical system. It's basically called cyber physical system. Okay, so you can see that I have given my information here, and then there's an email at the bottom. You can email me. As I said, normally I'm looking for students with some, who are interested for PhD. Okay, so this is the intro that we're going to talk about it. So imagine a world. Okay, this is what is going to happen, right? So this is taken from National Science Foundation by David Corman, and you can see that you have a building we call earthquake-proof building. It's a smart building. Okay, and a smart building means it can withstand. They're using smart materials. Imagine that the wall, if the wall is going to break down, it should inform you, just like a human being. There are symptoms, it communicates. Okay, that's the goal of it. Okay, so smart building is something, it is really smart. You know, like a human, it tells you, I'm having, you know, fever, like a baby, kind of a thing. And then you have the smart cars, okay, and you have the energy efficient power grid, which we call smart grids, okay. And so you can see that there are intelligent water resources, even a person with a pacemaker, a smart pacemaker, which for a heart. So imagine that this is where the future is heading, actually. Okay, so in order to get that, this whole thing, each of these systems, we call them as smart cyber physical systems. So cyber physical systems, the word cyber physical systems were been coined in 2007, and I'm going to tell you a little bit about that. Okay, so what is a cyber physical system? So cyber physical system integrates computing, communication, and storage capabilities with monitoring and control. Okay, so CPS transforms how we interact with the physical world. So what does it mean? So let me skip this slide. Okay, so here is what is a cyber physical system. So you have a cyber component here on the left hand side, and you have a physical system, and each of these, this connection can have a wireless network, can be a wired network, or a physical connection. It could be either of them. Okay, so this is what a very a dumb man's explanation. So embedded, it's different than embedded computer systems. So all these examples, like connected vehicles, you have the smart grid, you know, so any transportation networks, all these are connected, you know, they call cyber physical systems. Okay, so so what is characteristics? Cyber is integrated pretty much in every physical component. All right, and the most important thing is they operate at multiple time scales, spatial and temporal. So the question is, you have two loops in like a control. You have two loops. One loop is sampled at milliseconds, let's say. The other one is sampled at once an hour. So that is the time difference, you know, between the outer loop and the inner loop. So that's what we call spatial. Okay, and there are multiple temporal and spatial. Spatial means basically, I don't know how many of you know partial differential equations. Most of you have studied ODE. ODE is very common. We all like ODEs. But PDEs are more harder. Now, what is the difference between a PDE and ODE? What is the difference? I'm positive you guys have studied even in undergraduate. And what is the difference between a PDE and an ODE? You know what ODE and what the word ODE and PDE? What does it stand for? Partial differential equation. So what is the difference? So one is with respect to time. PD is also with respect to time, but it's also with respect to space, either x, like the distance. So if you look at the heat conduction, and that is basically with respect to the x, y, and z, for example. So spatial is each x, y, and z. X is varying with respect to time, y is varying with respect to time, and so that's where it becomes partial differential. Each of them you take a partial. So spatial, it can also vary with respect to space. This is where I said you got to have the map background. Remember that. Okay, and the other thing is operations that you do, it has to be dynamically reconfiguring. That means it has to organize itself and all that. That's a cyber system, and the operation has to be dependable. Somebody said, you know, he does something for control for aerospace systems. Imagine if those systems are not reliable or dependable, you can't fly on a plane. So secure, that's important if you are a you know, computer scientist, but it's also important for control person also. And then the other thing is safety. So a lot of times we want these systems to be safe. So that's also very important. So cyber and physical components are tightly integrated. They have to be connected together. If you remember, I showed you. So here you can see that left hand side has to be connected to the right hand side. The mouse doesn't work here, so I think the left and right, this and this one has to be connected properly, and it has to be integrated. Okay, so that's mainly what it is. Okay, so little history here. So if you look at it, let me see if I can remove this off. I'm not able to remove this off. Yeah, I don't know. So this is from real-time systems to hybrid systems. That's the title. And you can see that 1949, the computers are basically, computations and in 1949. In 1973, there is the topic of real-time computations. And hybrid systems came in 1990. Hybrid means both continuous and discrete mathematics. Because computers work in discrete domain, and physical systems operate in continuous domain. That's why we usually use them to we describe the behavior of a continuous system, any process, by ODEs or PDEs. And then you can see that around 2000 here, around 2000, you see that there are people that they coined the word what we call cyber physical systems. Okay. So from communication, acting and control, I think this guy is blocking the title. I don't know, you may want to remove that little thing in there. Can you remove that out? Otherwise they can see the title in there. So the communications and control perspective, you'll see that people, that'd be good. I don't know why it is popping up. It shouldn't pop up there. Or you move that, if you can move it outside. Yeah, just move it to the. I think if you have a mouse, that'd be good, because you can project out on there. Yeah, go ahead to the full form. Let's go to the full screen. Yeah, the mouse is good if you have it, because then I can point out. Sometimes, it's not there, but that's okay. So I think you can see the. So this around 2006, this is how it kind from real-time systems to hybrid systems. So from communications and sensing and acting, and you can see that there is this communication side here. Yeah, if you have a mouse, that'd be good. I think because. Yeah, let's see. It makes it easier. That's good enough. So you can see here. So here you can see the communication side, the cellular networks, and you have the sensor networks. And then earlier there is a convergence of communication, computation, and control, and it becomes what we call networked embedded systems. So this is how the cyber physical systems came in the word actually came in from different domains. Okay? So, and if you look at control, if you are a control person, okay, so you see that the first level of control is basically analog control. Then the second generation of control in 1980s is called digital control. And then now we have what we call is there are some network protocols, networks being inserted in the control loop. That's why we call that as a network control systems. Okay, and the minute you have a network has a protocol. So if you guys email, right, remember when you send email, what protocol does the network uses? Huh? No, HTTP is the web thing. Huh? TCP/IP, the transport control protocol. So, and we won't have time, but there is in the book it talks about how to bring that stuff in there. So basically you have a protocol, and that protocol has packet losses. Those packets go like in packages, kind of a thing, like you are sending so your message is broken down into different packets, and those packets go through the network, so it's discrete. And so whenever there is a packet, things get dropped. So there is delays, and there's also quantization. You have to limit the number of digits. Okay, so this is basically led into what we call event trigger, event plus time based. So this is the third generation. The network control systems is the third generation or the fourth generation of control. Okay, so if you need to do the cyber physical systems, you need all these background. It's an interdisciplinary field of computer science, control, communications, software engineering, and networking. So if you look at it, there are different degree programs in the US, and those degree programs, they offer like a certificate or course on cyber physical systems. So it's unlike the electrical engineering or computer engineering, you have to have the cyber physical systems. Okay, so cyber physical systems are deeply integrated. Look at that. There is a transportation. Okay, there is this transportation field, energy, industrial automation, healthcare, and critical infrastructure. So they all can be called as cyber physical systems. That's where in the future. That is the future. So you can't have these silo degrees like electrical and all that. What industries are looking at is basically having somebody in control, communication, software engineering. That's what is needed as future job opportunities. So one of the examples is make cities smarter. They call smarter cities. Even in India, Modi and other prime ministers, they talked about smart cities, right? You might have heard that. So basically smart cities, you have parking, and you don't really use an app, and basically it tells you when you are in that area where is your place to park, and you go there and you park it. So you don't pay, automatically deducted from your bank account. So many stuff going on. So you have the PEVs. So everything this is kind of a smart city, smart grid. Now imagine you have a wireless area, wide area network connected with a server, and you have the smarts, all the different generators, smart home. So the idea in a smart is able to heal itself if things break down. It motivates customers to participate. It resists attacks, people trying to attack. It accommodates all generation options. So if you are a power person, you should be able to accommodate renewables like wind, solar, okay, and the traditional diesel engines, and it's able to run efficiently. So a smart grid delivers electricity from suppliers to consumers using two-way digital technology to control appliances. So you can see that it's a big deal. Okay, so in the future, the industries are going to look at not electrical engineer. An electrical engineer who has taken a course on compilers and software programming, who also knows how to do, networking. So imagine that. That's what is expected as a future engineer, not like the electrical old curriculum we have studied. And those things will go away in a matter of time now. Okay. So this is a picture of a smart grid again, and you see that it's envisioned that the smart grid essentially will likely have a control system that analyzes the performance using distributed reinforcement learning. And we're going to talk about that. The whole course will talk about it. So network enabled manufacturing. So this is the projects with Boeing that I have been involved, and my network manufacturing, everything, all the tools, everything is connected through a wireless network. So whatever I'm doing, it's automatically records the information. Okay, and they have RFID tags. How many of you heard of RFID tags? How many of you heard of RFID? Yeah, what is an RFID tag? Okay, let me help you. The RFID stands for radio identification detection, right? RFID, radio frequency identification. So it's a little chip with a wireless connectivity. You know, it looks like a piece of paper with a little digital circuitry on it, okay? And you put it on anywhere, and it will tell you what the name is. So what we call that as a cradle to grave. So it starts when something is born, a product is just born, and you monitor the life of that, and it's stored on that. There's a little memory. It's called a mobile database. Okay, it's a mobile database, and it goes with the part until the part breaks down. And the thing is, it saves like a human. Imagine you have a patch. I don't know, some of you know that in medical area also. And that patch is saving all the life, like the heartbeat, everything of us on that patch, so that anybody can, if somebody faints and dies, you know, Abdul Kalam fell down one time, right? And so if anybody has any health problems, you can actually read so that somebody else can treat it without having somebody carrying all that paperwork. Okay, so it's an RFID tag, is widely used in aerospace industry. So we were doing this in 2000, and we can also look at real-time systems. So most of you know real-time location systems, GPS, right? And what is the problem with GPS? Huh? One is accuracy, but does GPS work indoors? Huh? No, it doesn't work indoors. It's not good in indoor environment. So real-time location systems are mainly systems that are like GPS. What will happen indoors? Indoor environments. Let's say you have a mobile robot and you want to track a path. So they have used all kinds of other things, technology like IMUs. Have you heard of IMU? Inertial units, right? They use that with some dead reckoning. And so the main reason is because you cannot position, you don't know accurately what is the location of that. So basically, you know, we are looking at in 2000 things that you can locate indoor environment because GPS is unavailable. Even outdoors, some places you won't get GPS. Okay, so there are a lot of opportunities for cyber physical systems. Pretty much everything is a cyber physical. Self-organizing factories. This is what is going on in the future. Embedded intelligence. I usually play a video of this future. Unfortunately, I don't know whether I have a network connectivity, so I didn't play the video. There should be a video, you know, there are a lot of videos on my website. So there is a video that maybe we have time, I can bring my laptop and we'll do that at the end of the course, you know. And embedded intelligence. So this is another important, so there is the RFID tag with AI going in each of those tags. This is embedded as part of the physical system. So basically you are proliferating all these physical systems with these embedded with some machine learning component in there. That's what is happening in the future. So if you are an engineer and you want to be successful, you can't take courses just in electrical engineering. And as I said, you have to have the background in software engineering and other things. That's how it's going to be in the future. Otherwise, you will be outdated pretty fast. You'll be outdated. This is what is happening. Okay? So smart systems, from sensing, computation and control, they're all integrated into one another. Okay, so we call that as informatics or smart healthcare. So this is what is happening even in India, for instance. And that's the future, what's going to happen in the future, okay? Smart environments. So, you know, like for example, I can control my home temperature from here in India. I have an app, I can even open and close the doors of my home. I can control it from here. If I have a network connectivity, if somebody is waiting to get in, I can actually open the door. And my home is captured with cameras, okay? There is a monitoring. I can turn it on. If somebody is a maid or somebody is coming in and she comes to clean, I think it monitors. So I can do it even I'm in India, for example. So those kind of systems are currently exist. And this is not too far that you're going to see at homes. And in the smart homes, you see that there is a solar on the roof. It basically provides electricity not only for the home, and it basically sends the electricity to the grid. So you can actually sell the power to the grid and you get paid. And in the night time, you can use the electricity you buy from them. So there are a lot of things are going on. And it's not too far that you're going to see these things in real life. Okay? So keep that in mind. So then cyber infrastructure. Already Vande Bharat Express. So you can imagine now there will be a lot of automation going on, right? To prevent two trains colliding. A lot of stuff. Bridges. You remember already you have those fast tags, right? You remember that's an RFID tag. Like in the track goes, you pay automatically, they deduct from. So those are RFID tags. You have it on the car and it reads as you come closer. So there are a lot of things that are getting automated. So remember, guys, it's not too far. If you are young than me, okay, I'm telling you right now, 20 years past. I haven't told you what is going to happen. So if you're a double E, within 10-15 years you will get outdated. Unless you update yourself. That's what is happening. So as an electrical engineer, you got to have software background. You also have to have some courses in computer science, some courses in mathematics. I think we were already talking about it. Okay? And Internet of Technologies are going to play a significant role. IoT basically brings in the idea of a sensor with some sort of a network. Very small, you can measure a lot of different things, okay? And they are placing these in appliances, vehicles, buildings, cameras, pretty much everything. So cyber physical systems, there are degree programs, new degree programs are being offered, just like electrical. And the funding agency in US, they changed the name to cyber. It used to be electrical and physical communication systems. They changed the name to cyber communication and control systems. So the names have been changed now. So you remember electrical department in US is called electrical and computer engineering. Now it's being changed to cyber. A new set of courses. So remember how many with AI coming in, people are getting laid off. Both software engineering, that's what is going to happen, guys. If you are young, take courses now. Okay? So you ask me my background. My bachelor's is in electrical engineering. Master's is in computer science. And PhD is in robotics, which has the blend of computer science. So I was one of the very early ones who was studying, learning AI. I took so many courses. During that time, people never heard of that in the 80s. Yeah. And you see that Google and all these companies laying off. It's going to happen. India will be affected. India is in a good place because a lot of young people. And most of you, if you are interested to learn, this is the way to go. Yeah. All right. So new set of courses. So, but there are a lot of opportunities. If you have an open mind, there are a lot of opportunities, right? IoT, energy efficient building, smart grid, plenty of opportunities. Okay, smart healthcare. So there are a lot of opportunities in healthcare. So opportunities are abundant, provided you have improve your skill set. Emergency response, security field, and so forth. So why is that a lot of opportunities? How many of you heard of big data? This is a very new term, big data, a few years ago. So what generates data? How much? Complex systems, smart environments, fleet of vehicles, process control, smart grid, they generate data. How much data? So if you look at the data that these things generate, Boeing jumbo jet, when it crosses from, so like the flight I took from US to Europe, it generates about 650 terabytes of data. Terabytes of data. a human activity generates about 1 gigabyte of data. So imagine you are accumulating the data, it becomes big data. So one sensor generates about 2 megabytes. So all these things coming in as part of cyber physical systems. So what makes big data, Microsoft defines big data is basically is a process of applying serious computing power. Massive and highly complex sets of data, okay? Data in rest, data in motion, data in many forms, and data in doubt. So there's a lot of needs for cyber physical systems, new calculus. So when we talk about cyber physical, that means you're talking about new fundamental science like ODE and PDEs. Okay, dynamics at different time scales. There are delays. These delays are random because the network that you're operating, a computer or a communication network, basically that's modeled as a stochastic system. Most physical systems are modeled deterministic. So there's a difference between a deterministic system and a stochastic system. What's the difference? What's the difference? I know many of you are master degree students, and all these things we studied in undergraduate. Right? We studied this in undergraduate. But what is the difference? So there is some variability. So it won't show the same behavior every time you start, right? So there will be some variability, very fundamental, very basic. So the process variables vary with respect to, it is basically varying in a distribution. In a deterministic, you don't have just one spike. In a stochastic, it has some sort of a distribution like a, so it's varying with respect, it has a mean value, it has some variance. Okay, so all the process like the computer networks, the wireless networks, they are defining them as random variables. Okay, so you'll see that when you run the code in the labs, you'll see that you won't get exactly identified results because when you're running it next time, you're initializing it, and so when you initialize it, there will be a random seed, and that initializes at different values. So this is very important. Okay, so the delays and packet losses. So usually in that network, you have some delay, and those delays are random. They are not deterministic. You can't say every day, let's say you're going from your hostel block to, or from your home to your campus, you can't exactly say it takes 15 minutes. You know, one day it may take 15, one day it may take 1 hour. Some days you may take half a day if there is a accident, and some days, you know, you will take 10 minutes plus few seconds. That's the variation you're talking about. So any time when you have a continuous system and a discrete, we call that as a hybrid system. Okay, the time is not global because each system has its own time, and time is local in this case. So you have to have a software and hardware co-design tools. So this is why I told you, even if you're a EE student, and remember, I am actually at the end of my, maybe another 10 years I can work. So if I would have been in India, all my friends are already retired. So I'm considering myself as a super citizen, right? 58 is the retirement age. 60, maybe if you work in IITs, they go up to 65. Okay, but remember, in US there's no age. You can work for 95. So you, and people are, a lot of faculty that I know of, they're already like 78, 80. I have a faculty member, one well-known guy in Yale University. He said he's 92. He's going to have a birthday. He called me and said, let's have a symposium on adaptive control. He's a well-known guy in adaptive control. So 92 he is. So what I mean is, I don't know whether I'll survive that age, but remember, if you're really young, you really have to have all these skills, otherwise you will be out in 5 years. I don't know whether you know, recently, what is that, Narayan Murthy, I think in that Infosys, they fired a few people, they are not keeping up, and I'm telling you, this is true. I've seen about a large quantity of Indian students coming out to a lot of colleges, don't have the skill to survive. Let me be blunt on that. Yeah. There's one thing to study a course, get a grade. I don't know, here you get gives in A, B, C, D, or do you give them in percentage? Grade is there, okay. Grading system. So you can get a grade, but that person doesn't know what ODE is. So I did my undergraduate in 80s. I still remember all those differential equations. I can actually solve those differential equations. Yeah, you should be like that. So there are a lot of things you study, but you have to have, you need to know how to do it. That's important. The skill is very important. Okay? So I think that's the software and hardware. That's a pretty common thing. You got to have it nowadays. It's given. It goes without, there's a word called goes without saying. You got to have that. Otherwise you will not survive. Okay? So there's also issues now when you bring in computers, there's also an issue of security and privacy stuff, right? All that also is different from a cyber physical system because these are real-time systems. They're running in real time. Even computer science people cannot handle these. You can't use some of those. So that's why you have to have a separate degree programs in these systems, okay? I'll quickly going through. So security and privacy, these are not legacy systems. So you can see that they have to come up with different new stuff, and this is a real-time system. So if somebody putting an attack on a computer network, in a worst case, if the computer hangs up, what do you guys do? When computer hangs up, what do you do? You switch it off. But you can't do that same thing with a lot of real-time systems. You can't just go and bluntly go and turn it off. Things go out of really, like in a car, imagine. You turn, suddenly you're driving at 50 miles an hour and you can't turn the car off. So there are a lot of things like that you can do if it is a cyber physical systems. So even a computer science people, you have to have skills. So they are studying in real-time systems. They talk like an undergraduate student, and I keep telling them, all this is done in 80s. So you have to have they have to learn also skills. Okay? So now, a network control system. So what is a network control system? So network control system is a small subset of cyber physical systems. So you can see that here you have a controller. In the traditional world, you have a physical system. These two are physically connected with a hardware wire. Now you see that on the left-hand side, you have different physical systems, the controllers, and they're all connected through a wireless or you have a wired. So a good example of a wired network is a automotive vehicle. All automotive vehicles has a bus, CAN bus. It's called Controller Area Network Bus. And that bus is basically IEEE. It's a standard in there. And it uses some sort of a protocol. Okay? So what is a protocol? Protocol is a way of communicating. So let's say we all are here. Imagine when all of us talk at the same time, what will happen? What will happen? If all of you talk at the same time, what will happen? Nobody will understand anything. The same idea. So if you have a cable, if all the subsystems are communicating at the same time, they all collide, nobody gets the information. So the protocol is a way of exchanging information in a systematic manner. And it has a performance so that you want to keep that bus operating at 100% or 99.99%. That's what a protocol does it. Okay? So network control system is a network is inside a control loop. And that's what basically called network control systems. So all the distributed systems essentially has a network. Okay? So you can see that in a very simplified, you see there is an actuator, there is a physical system. The physical system has a sensor. You sample that, you quantize that information. You see that dotted line in between is the network. So you can see that this is the network in the middle, and you have the wireless or wired, the delay and packet losses, and you have a controller in the feedback loop, and you have a control quantizers. So the controller is outside the feedback loop, and then it goes through the network again, and it basically becomes a packet goes to the actuator here. So the network is in between the physical system and the controller. Such a system is called network control systems. It's connected through the network. So when such a system exists, you have issues like network control system, you have packet delays. If I can find my mouse here. So you can see that there is the network induced delays. Okay, so the delay, you see that the taus are called delays. Then you have packet losses. The gammas are packet losses. And then the quantization errors. So what happens is when this measurement value, temperature like 50 degrees, that's quantized when it goes to the network. Quantized means it has finite number of bits. There will be round of errors. And that information goes and becomes a packet. So that's what is called quantized errors. So if you see that at the bottom, you see that you transmit the sensor, it takes so many seconds to receive it at the controller. Controller generates a packet, it takes so many seconds to reach the actuator. So this time is called the round trip time from the sensor all the way to the actuator. And that time is random. So sometimes that packet gets dropped. So when the packet gets dropped, the network when the network control system operates in what? When the packet gets dropped, what will happen? It will not transmit. So physically it becomes what? Open loop. It becomes open loop. Even though you are physically connecting a network, there's no information going in. It becomes open loop. Now, I know most of you have some controls background. Why do we always prefer closed loop control system? And why do we like closed loop control system? Why not run the system open loop? Right. So there is a performance. So you look at a performance. Why open loop control systems we don't like it in terms of performance? What will happen? Or did somebody tell you why do you need a controller anyway? I can just simply close the loop. Why do you need a controller? One at a time, guys, because remember the same thing I said. So why do you need a controller? To have the desired performance. So even the system is stable, it may not provide you the right performance. And how do you define performance in a control system? How do we define performance? Huh? How do we define it? Yeah, performance indices. Let's say very simple basic is there is a transient performance, there is a steady state. Transient is overshoot, undershoot, settling time. Steady state is basically steady state error. Don't forget that. Those are undergraduate material. So those are the performance. So open loop, even though the system may be stable, you still need a controller in order to make sure that it maintains the performance. So open loop systems may not meet a certain performance. That's why you need a controller. Don't forget that. Okay. So here the system, even though physical system is deterministic, because of the network it becomes stochastic, the overall system. So this was discovered. So all of us were struggling. So this was one of the classical papers we published in Automatica that models the whole system into a stochastic, and you will see that hopefully tomorrow. So here is a simplified representation, and here is the paper that I cited, published in 2012. And you know what? Most of us are familiar with linear systems. I'm going to show you that. So if I have a linear system, a continuous system, x dot equal to ax plus bu, okay, and if I have to bring in the network delays and packet losses, then I do a little mathematics here. okay, and I bring in all that stuff and I'm discretizing it, and you can see that this operator equal to 1 when x is greater than 0 equal to 0, there is a bound on delays. So if I do the mathematics, then the same linear system becomes discrete. Look at that. It becomes discrete. That is a model or a behavior of a network control system. So when you model it, it becomes discrete, and you see that the A matrix here, the A matrix is a function of delays. You see that D bar is a delay. And you know the gammas are packet losses at the time instant k minus 1 k. So that model, A and B matrix, becomes random and stochastic. When I say stochastic, it's a function of random variables. What are the random variables? The random variables are network delays, packet losses of the network. Even the computer science guys doesn't know this, or even communication people. So this is what the technology is. So now look at that. This system that I showed you, this is a deterministic system, A and B matrices. When I'm enclosing it by a loop, and AZK is a discrete time A matrix with random packet losses and delays. So unless you have a mathematics, you won't be able to do this. And the mathematics is here. So it requires a background on stochastic, requires a background on linear algebra, it requires a background on digital control, where you take a continuous system and you are discretizing it. You need to really have to have the background like this in order to take that equation 1 and convert that equation 2. And you see the B, this B is also a function of the packet losses, and D. So we were the first ones to show the world how to model this. So you see how this guy, a Chinese guy, is a very famous guy, and that is his PhD work. He's known for that, and that's why he's this author of the book. That is his PhD. He's written 17 transaction papers. So you see that a PhD, how it comes out. Yeah. So each of my students, a PhD student, has a legacy. He goes with some name, like, you know, his area was network control. So that's how he becomes an expert. So this is his work, fundamental work. How? So until then, nobody knew how to take a linear system, and people were doing all ad hoc stuff. But how to take a linear system and actually have these network protocols, how does that work as part of a network control? So that's what we're going to use in your labs. Yeah. And you know, this since it's a random variable, the packet losses delays, you have assume a distribution. And they vary in that distribution. Since they're varying, this A and Z also will be varying. Now let me ask you one question. Do we know the delays and packet losses? Do we know the delays and packet losses, guys? Do we know gammas? So D bar is the delay, gamma is the packet losses. Do we know that values? We don't know that. You can assume a distribution. That's what I said, the assumptions. You can say it's a normal distribution or some other distribution, right? The random delays and packet losses. But then since those are varying, what will happen to AZK and BZK? Even though my A matrix and B matrix I know very precisely from the process that I'm controlling it, I want to control, but AZK and BZK I don't have any clue. Why don't I have any information? Because the gammas, you see that this is at k minus 1, the delay at k minus 1, delay at k minus I. So the k minus D bar is the time. And the gammas can vary over time. So therefore, I don't have the AZK and BZK. I don't know. I don't know simply. So even though I know A and B matrix very precisely, at the end, I may not have AZK and BZK. That's the problem. Okay? So, when gamma becomes, when there is a loss actuator, it becomes open loop. When it becomes open loop, the gamma becomes 0, so some of those values will become 0. The system will become open loop. Remember that. Okay? Any questions? What is a network control system? You see that now. So, because of the network, okay, so because of this network, you see that this controller information doesn't go through to the actuator. And because of this network, if there is a packet loss, the sensor information is not fed to the controller. So therefore, the controller and the plant, even though they are connected by a wire or wireless, nothing is going through the network. It becomes open loop. Okay? So this is what is called a network control systems. So the losses, packet losses, delays, the delays are random delays. That's why it's become stochastic. Any questions here, guys? Any questions? So AZK and BZK, you don't know. We won't have that information. So now when we don't know the AZK and BZK, how do we design a controller, guys? How do we design a controller? Like you designed, like, root locus and all, right? Remember that in undergraduate? I know some of your masters. Did you guys take a state variable course? Right? So when we design, do you guys know Ackermann's formula? What is Ackermann's formula? That's a danger. You nod your head. What is Ackermann's formula? That's correct. Go ahead. What is Ackermann's formula? So Ackermann's formula is U equal to minus Kx. Okay, or K times C if it's an error. Right? So K is the feedback gains. Very simple. Feedback gains, right? So now how do we determine the feedback gains? How do we determine them? Pole placement. So how do you place the poles? Now hold on, let's look at it. How do you place the poles? How do you come up with the poles of a system? But that is the desired pole, locations of desired poles. But how, you need to know where the location of the actual poles are. From the roots of the characteristic equation. So that means you need to know precisely the dynamics. If I don't know the dynamics, how are you going to come up with that? You see? So I cannot design a controller because I don't know the system dynamics. So if I do let's say by chance if I try to come up with a transfer functions, right? That's what we normally use. If I don't know those locations of those A1, B1, that means I don't know the location of the poles. I can't come up with a design. So you see that that's the PhD problem. So if you're a PhD student, you should be looking at problems like that. So it's a linear system, and even though it's a linear system, basically I don't know those dynamics, so that's where you got to use what we call adaptive control. And adaptive control, what it does is, it estimates something, and then using that information you are controlling it. Okay? But there's a difference between learning and adaptation. Nobody is going to tell you that, because nobody knows that. I'm telling you right now. Somebody who worked in this area knows. So what is the difference between learning and adaptation? We all do that as a human body. As a human, we do that. We learn and we adapt. But what is the difference? What is the difference? And what is learning? What's learning? Guys, this is not a simple question. Even faculty, many of them don't know the difference. I'm telling you. So what is the difference? a learning and adaptation. Because in adaptive control, some of you said, right? So what do? You assume A and B unknown, and you basically estimate it, and then you use it in the controller. That's what we normally do in a traditional adaptive control. But, so then why are we using machine learning? What is the difference? Okay, this is your homework. So you're going to come back and tell me tomorrow. I'm not going to tell you today. As I said, a lot of faculty don't know. 90% of them doesn't know, even control. No, you can still do the same adaptation. Adaptation is supposed to do that. Okay, so that's not the reason. That's why I said 90%. You can check with your advisors. I assure you, unless they've taken my class or something. Yeah, this is what the skill set, what I'm talking about. There's a huge difference between learning and adaptation. Yeah, okay. So we'll talk about that. I won't go without telling you the difference, okay? All right. So there is also stuff that can come in event triggered, and at the end of the course we talk about that as well. So basically the problem with these networks are, these networks you can see has a finite bandwidth. So there's only so much you can send. You have a pipe. A network is like a pipe. You are sending water through it. There's only so much water you can send it. And how much water can you send in the pipe depends on what? How do you determine how much water flows through? A capacity, but so what is that in volume? Remember that? So there's a capacity that how many packets go through. It's very similar. So most of the networks have finite capacity. And if it's a wireless network, it's even less. So when you don't, if you're sending a lot of samples, because you're sampling at a very high rate, then you're sending the same feedback, like sensor going through the network and the control packets going through. Sometimes the packets can get dropped because it has a finite bandwidth. Okay, so don't forget that. Okay, so what will happen is there's a new type of control called event triggered control. So typically we assume that the sampling rate is determined by Shannon's minimum 2 times that, and in control they say you basically determine by 10 to 20 times the closed loop bandwidth. Okay, this is kind of ad hoc. So event triggered control basically kind of threw that out and say they call that as a performance based sampling. So what it means is basically I can leave the system in open loop, and the minute the system is becoming unstable, then I suddenly close it. So by doing that, what is the benefit? What is the benefit in a network control system? You can reduce how many packets are going through the network. Right, you see? You can reduce. So right now you can say 10 times the bandwidth, you can still be in kilohertz. Sometimes, that means you are sending so many packets and you don't really need it. So, so now this particular one, event triggered, you see that there's a network. If the sensor is constantly transmitting, and instead of doing that, you have a switch. The switch closes and opens based on that performance. And by doing that, you can still show stability and the same set of performance. That's called event triggered. So you have an event based on certain performance, and it basically closes the switch, then it basically you transmit a packet. There's a lot of work happened in event triggered. That's a separate book that came out last year, 2024. There's a book that you can look at it. Yeah, all right. So you can see that here, you see these are spaced at equal intervals. This is what we do now. And here you can see the duration varies here. This is called event triggered control. Okay, there's a lot of work going on now. It's now older. It's basically an old technology now. Okay, so they use what they call a zero order hold. It's called zero order hold. It holds the value until a new value comes in, and then you basically do that. Okay, so I'll skip all this. You see that this is the Ackermann's formula. U equal to k times x of k. All right. Okay, so I'll skip all this. So let's go into, let me go into another set of slides. So now I'm going to go into, that's a basic introduction of network control systems. So while I'm pulling up the real reinforcement learning, do you guys have any questions? Do you guys have any questions? What is a network control system? That's what I explained. And it came out from cyber physical systems. So if you talk to people in cyber physical systems, people know that by now. Okay? So cyber physical systems has got a lot more stuff. But network control is basically the small stuff that for control people. So yeah. So what is any questions on what I just covered so far? Tomorrow there will be a lot of stuff goes very quickly with mathematics. So you may not understand everything, let me tell you. And don't even imagine that you will try to understand it, because you learn major things. You have to take a formal courses. So I'm going to, in this one, I'm going to cover a few other basics. Okay, any questions? Yeah, go ahead. D-bar, some delay bound. Because you really don't want the D-bar to go to infinity. So why is that? What will happen when D-bar goes to infinity? It becomes open loop and you are not really closing the loop. So basically, you cannot operate a system open loop. Remember, if the system is inherently unstable, then you really need a feedback. So you can make the system stable, and that's why the D-bar has a finite value. You know, the bound is finite, but within a bound, things can vary. Any other questions? Yes? That's correct. Right. So you can even still consider the network control system as a different time scale, because you know, you could even there is in stochastic control, stochastic systems, there is a stationary process. Remember that. There's also non-stationary. What is non-stationary meaning? I know we studied this in undergraduate. All of us do that. But you know what happens when the math professor teaches that? It goes above it. We think, oh, it's not needed. So stationary, what does it mean by stationary? Even in stochastic processes, we study that. What is meaning by stationary versus non? And that's what I'm coming. So what is, to answer your question, what is stationary, what is non-stationary? Stationary means it's not changing over time. Time invariant is basically in stochastic. They won't call that as time invariant. They call stationary. That means you take any piece of time, the properties of that would be same as any other time period. But if that property is changing, like the distribution and everything, it becomes non-stationary. So the same behavior, what happens is, you could have in the process multiple levels. Each level might be operating, one of them is operating once an hour, other one is operating in milliseconds. You see? Yeah. That's where the time scale is coming in. Any other questions, guys? Any other questions? And don't feel shy. Let me say this. I don't know. This is something I learned. I never asked questions. I used to be very shy, and I realized that some of the questions, probably what I was having in my mind, were very difficult. So I'll tell you something I learned in my so many years of faculty life. As somebody who is asking, you think that guy is dumb. Sometimes those questions are difficult to answer. You'll be surprised. Yeah. So quantization means, let's say you have, remember, then computers operate a certain number of bits, like they have byte, right? So let's say like you're using 8086 processor or like a Pentium processor, they have a certain word length. So sometimes it's a 16-bit, sometimes it's 32. So you take a value like a temperature or a pressure, and you are digitizing it in the number of words, in the number of bits. That's what is quantization. So you don't have infinite number of bits to quantize that value. 1.66666, let's say. So round off, right? You round it off to 1.67. That's basically what is quantization. We're going to talk about that. So we'll do that. Quantization is one of the chapters, we'll look at it. You see? And that creates some error. Okay? So that's an additional thing that, so you're taking, you have a finite thing and you are writing that, let's say 1.66666 something, you're truncating and writing as 1.67. Yeah. Okay, any other questions, guys, before I get into reinforcement learning? So this is how it quickly goes. Okay, because it's a 2-week class, that's basically. There's a lot of stuff behind, we talked about it. So don't forget, you may want to think about it, what is the difference between learning and adaptation? Okay? So you ask or you Google and you come back to me, and I want to see that. Okay? So any other questions, guys? Okay. So I added this topic. It was not in the lecture because I realized many of you probably won't know much about reinforcement learning and stuff. So unless you take a course on some neural networks or machine learning, how many of you have taken a course on neural networks? So no course on neural networks. Do they offer here NIT Rourkela? Okay. No. Okay. So we do offer that, and it's a required course in undergraduate. Neural networks. So even computer science they do offer. Yeah, it's very important. So we'll talk about this, okay? And this will gives you some background on reinforcement learning. So there are 3 forms of learning. Remember, I am told you what is the difference between learning and adaptation. Okay? So I'm just going into, that's how people do. Remember that. All right? So there are different forms of learning. One is called supervised learning. That means somebody is teaching you, holding your hand, and you know, remember when you have a small child, you hold the child's hand and we write, right? Namakaranam, we basically write the name. So that's called supervised learning, okay? So people use, these are targets, okay, and P1, P2 are the actual output of the network, right? So basically the goal was the actual output should be close to the target values, okay? Then we know the network has learned. Now the targets, people use that, we call targets, the computer science guys call labels. So if you talk to people in computer science or AI people, they talk, do you have a label? So a label means basically a name or a target value. Okay? So you need that in order to develop what we call supervised learning. So use the error and then you're adjusting the weights of the network, and that's called supervised learning. A reinforcement learning is a classroom environment. Now, you have taken courses, right, in NIT Rourkela or some other place. Now, a professor or a teacher teaches you something, then how does he assess whether that material is understood by students? How does he do it? You're conducting exams. Now, those exams are not holding your hand. Remember that. He periodically say, in my course, you take 3 exams, you have 10 homeworks, right? And the homeworks are basically graded a little more frequently. The exams are fewer, right? 3 exams or 4 exams, whatever, and you have a final exam. So what do? You get a grade, and then once you get a grade, what will happen? Somebody gets 60, somebody gets 90. So what is the difference? What's the difference? 90 out of 100, that's what I mean. What is the difference? So in terms of performance, somebody who's getting 90 means he's doing better than somebody is getting 60. And that's what is reinforcement. So what happens if somebody getting 60 immediately has to have a different plan? So let's say in the first exam that person didn't do well. So what does he has to do? In the second exam, you better prepare something differently so that your score will be from 60 to 90 or whatever. So that form of learning, it's not like holding somebody's hand and you're adjusting. So the professor won't tell you, right? I won't tell you what you need to do. And what I tell you may vary from one student to the other. Okay? So I can tell you something, but that may not apply to somebody else. So that basically is called reinforcement learning. So you're really not told how to do it, but you will be given a score and you use that information and you have to adjust yourself. Humans do all the time. All biological organisms like snake or you baby. So how does let's say that baby or something, remember when we were babies, you touch something hot, you remove the hand. So who tells them that it's hot, you need to remove it? Who tells them that? Who tells them? Nobody. It's a reflex. Sometimes people call that as a reflex. So a lot of times people learn differently. In each of you, probably I can't expect you to learn everybody the same way. All of us learn differently. Just like all of us have different height, different weight. Yeah. So reinforcement learning, we'll talk more about it. Unsupervised means you have different outputs and you cluster them, different forms, like you can say all women have certain characteristics, all males have certain characteristics. So that's basically we cluster them, or people with different height, for example, you can cluster them, different weight, for example. So that comes under what we call unsupervised. So there's no supervision, but you basically do. Reinforcement learning, the only feedback is the score. How well, or 90%, 60%, what I told you. That won't be continuous. That is the score, you get it, and you use that information to adjust your strategy. Okay? So there are three forms of learning: supervised, reinforcement, and unsupervised. Now in control, we talk about online learning. We'll talk about it. So a lot of supervised learning is offline. The supervised is offline. Reinforcement learning is also offline. So that means it's not done in real time. But in control, we need to learn the dynamics in real time. So we do what we call real-time learning. We'll talk about that. Real-time reinforcement learning, okay? So what is reinforcement learning? When an infant plays, waves his hand, or looks about it, it has no explicit teacher. Remember, you look at a child, who is born, after a few months, the child, you smile, the child smiles back. Who is teaching that? Nobody. Probably some of you are young. When you have kids, you'll know. Yeah, you don't teach the kid. It smiles. This is very interesting things that you do, right? And you wave the child with the hand, you'll realize that the child waves back. You're not teaching the child. Sometimes parent may hold the child and you wave. But over time the child waves. So nobody is teaching that. Exercising the connection inside our brain creates a wealth of information. That's what is happening. Now remember, when we are babies, you ask your parents, if you feed a baby sweets, there's a smile on the baby's face. You will see that. You feed something sour, the child will not take it. You don't have to. You try it out. So a lot of medicines, they put little sweet in there. This is because of that. So that is basically generated. Nobody teaches a baby. This is a sweet, this is hot. Nobody. So all that happens with a naturally with biological mechanism. Not only just humans, snake, or even dog. Yeah. Nobody teaches that. We all learn by ourselves. Try it out, guys. You work with psychologists, he will tell you more than I do. Okay? So what we do is we study the computational side. How are these connections are formed? And we call that as learning. Okay? So a reinforcement learning from interaction. So I'm interacting with an environment, I learn from the environment. And it's also called goal-oriented learning from interaction. Okay? So what is reinforcement learning? Problems involve learning what to do. But you don't tell them how to do it. Remember that I told you. A supervised learning, you show them how to do it. But in reinforcement learning, you only do what to do, but not how to do. So how to map situations to actions to maximize a numerical reward. This is what I told you. If the student gets a 60, he has to think about it. how should he makes a 90 next exam? And no professor can tell you. You can say, oh, you study more. But that's all you can say. But he won't tell you how to study, how to solve problems. So these are closed loop problems, because the learning system's action influences later inputs. So this is what we use. A reinforcement learning is like a closed loop control problem. The learner is not told what actions to take. This is exactly what I told you. As in many forms of machine learning, but the student has to discover based on his own IQ. Okay? Actions may affect not only the immediate reward. So that means that if I'm studying for that exam, I may do well, but I may not do the next exam. You see, but they're all connected together. Materials from one exam may be connected, right? That's important, okay? So it is very important. So what is characteristics of reinforcement learning? It's a closed loop system, not having direct instructions. So nobody has a instructor to tell you what to do. They won't hold your hand, unlike supervised learning. Consequences of actions have a real big issue. If I make a mistake, it could be dangerous. Let's say that you learn driving, right? The instructor tells you, okay, you take a left, you turn the wheel, right? But remember, if you make a mistake, what will happen? You may hit something, and if it's a human, you may die. The guy may die. So it could have a serious consequences. Okay? It's often interactive. Interactive means you interact with the environment, like you are driving in a busy street. They'll take you when you are driving, and then you'll tell you take left, turn right. This is how they teach you to drive. Okay? So we call that as an agent. An agent must be able to learn from its own experience. So he can only teach you so much. Most of us ride a bike, right? In childhood. Somebody is teaching you for a few minutes, a few hours, but then after that you practice, right? And you learn. Sometimes in a hard way. You go and hit somebody, then you fall, you learn, right? So you don't really want to do that. Okay? So there is also called exploration where exploitation in a reinforcement learning. And we do all the time. Humans do. So let's say you go to a new place. What do? Huh? You explore. Even if you are in the same place, I'll tell you. And if you have multiple routes, sometimes you take a different route because let's say there's an accident. Oh, you realize that, man, I'm so fast. There's nothing here, no traffic. So unless you explore, you won't know that. That's a better route. So in reinforcement learning also the same thing. You explore, but unless you explore, you don't know. So exploit is basically what we call greedy path or greedy solution. That means that you have driven that route and you know that that's the best route, right? But unless you explore, you don't know whether there's any better one. So explore and exploitation. Exploitation means a greedy. That means already you have learned something out of it. Explore means you don't know that and you're trying one out of multiple. So this happens in reinforcement learning. Sometimes during exploration, you fail. You fail. So let's say you're controlling a plane. Do you really want to fail? No. Yeah. That's a big thing with real time. Remember I said that in my comments? So this is why there's a difference between the people who talk about AI and the people who talk about AI in control systems, because it's very dangerous. Okay? The same thing with reinforcement learning. So you have to really think about that part. So you have to discover actions, but you also have to try actions that have not selected before. But if you select some actions, that could be disaster, right? So agent has to exploit, and then he has to see whether the reward he's getting is better or not. If he gets a better reward, that means it's a better route or whatever, right? So the dilemma is neither exploration nor exploitation. Now, neither one of them you want to do it, you have to do both of them at the same time. Okay? So agent must try a variety of actions and progressively favor those that provides the best reward. Reinforcement learning is a separate course I teach. It's a full semester course. Okay, so I'm giving you in about 45 minutes. Okay? So it's a stochastic. So that means you start at different times, you get a different result. So it's all this learning is always stochastic. Okay? Key feature of reinforcement learning explicitly considers the whole problem as a goal-directed agent. So that's very important. So in a reinforcement learning, the goal is something, right? I need to do well. So what is your goal if you're a student? Is to get an A in the class. Now, is that the goal? No. You shouldn't be getting a goal like that. What is the goal, guys? What is the goal? Huh? To learn the material. But you know what? Statistically, people have shown that 99% of the students don't have that goal. Do you know that? What is the goal if most of the students do? To get what? That's all most of us do. All of us say that I want to learn. Remember I asked you this question. What's the difference between learning and adaptation? We adapt because we look at what the professor is going to ask. You look at previous exams and then you work out some problems and then you adapt. But you don't learn. So I know that's exactly what you need to. But none of us practice. I'm telling you right now. Yeah. That's the big problem why we are not successful. There's a big difference between learning and adaptation. Remember, I keep giving you will see that there are plenty of examples. Yeah. There's a huge difference, guys. You can get a grade. I'm telling you right now. It's easier, but it's very difficult to learn the material. When I say learn, there's a difference. So, you know what happens usually, when you really learn, I don't know in your student life, can somebody tell me? At least I didn't learn when I was an undergraduate student. I was the topper. But I really didn't get that enlightenment. That's called enlightenment. Till I started doing my PhD. Yeah. So that's when you really learn. There is an exam, I don't know, in these universities here, we call that as a qualifying exam. So in the qualifying exam, the students have to take in the second semester that exam. And it tests all your undergraduate stuff, all your undergraduate, okay? It's closed book, closed notes. You can't bring anything. You can only bring a regular calculator. No programmable calculator. So one full day exam. Okay? Is here? Even in IITs, I never heard of that. I think you should take that. And you know what? When I took in Georgia Tech, 1/3 of the students only pass it. We also have comprehensive, but that's different. I'll explain that also later. So qualifying exam you got to have. That's a mistake a lot of us do here. I'm telling you that. So there are, let's say I took my exam. When I took that qualifying exam, the department says that you have to take it in the second semester. So you have to, all of us have to take it in the second. So if you start in the spring, you have to take it in the fall semester. Okay, that's the second semester. If you start in the fall, you have to take it in the spring. No options, okay? And 250 students normally take, when I took that exam, about 45 to 50 students pass the exam. They give you 2 attempts. Once you have failed in the second attempt, you're out. You take your master's and you walk off. You won't become a PhD. And it'll test all your undergraduate, all your courses in undergraduate. You have some choices. Okay? You have some choices. So they'll tell you, you can pick 5 topics out of, like in electrical engineering, you have circuits, devices, which is, diodes, electronics, all that stuff. Then you have controls, you have communications, signal processing, power, okay? All that stuff, everything will be on the books. They'll give you 20 problems you are supposed to answer. You'll only get about enough time, 8 hours exam. You only get, it's not easy, guys. Let me say this. I tell you, it give you 8 hours, and you have morning session, afternoon session, okay? And then they take it, people get it in 20, 25. They take the highest, and they look at it, only they pass 1/3. Open book, it's closed book, closed notes. You can't bring anything. Whatever is in your brain, you're applying it. That's the learning part I was telling you. Try it out, guys. It's not easy. So unless you understand, remember that Ohm's law and stuff, we all studied, right? Right? Have you ever looked at it? How the Ohm's law has been derived? Have you ever thought about it? Ohm's law is a nonlinear equation. The devices, you know that the voltage, if we have studied that, it becomes nonlinear, the characteristics. It's not linear. Only we look at a linear range. Go back and look at it. Somebody said learning, right? You will realize that you never did that in your life. I can challenge you. That's why this exam was very important. If you don't understand that basics, you will not pass that exam. They'll give you 2 attempts. Typically, the second attempt, the chances are only you have about 50%. Yeah, this is based on statistics. So, you see? So that means you got to know the material. It's not the material you need to know. You don't have to remember those equations, but you need to know how those equations come in, what it means. And a lot of times, if you study, if you do a PhD, you are supposed to learn that. Then only you will come out with a good PhD work or a thesis. Yeah, otherwise you are not producing quality work. And this is a hard story, guys, but that's the way it is. Yeah, world is not nice. I don't know, you have seen that, right? If the students is the best life, guys. Let me say this. Once you come out as a student, life is not nice. Ask people who have, have jobs now. There are so many different things that you don't realize. If you are a student, enjoy it. Do well in your studies. That's what I would say. Okay. All right. So I will skip all this. We won't have time. Here is that typical block diagram that talk about it. This is the AI stuff, where you have an agent. You see that the agent sends an action, and the action changes the environment. Okay. We call that in controls, we call the state vector. It changes the states. Even in computer science, call that also states, So it's a state, then it also gives you a reward. Okay, but then you basically sense the state, then you adjust your action, and this is basically goes in a loop. So reinforcement learning is basically a closed loop system. And all humans do this too. All humans. Remember, you feed a baby some sugar, put it on that tongue, right? What will happen? The baby's face changes and he smiles. Okay, so you sense it, you accordingly act, right? And that's the reward. So the baby all of a sudden crying, you feed some sugar, stops crying. So basically an agent in this case, an environment is unknown. Look at that. Non-linear and potentially stochastic and complex. A policy, we call that as a policy. Policy is a mapping from the states to action. It's called a policy. So control is basically a policy. So U equal to Kx, X is your state. So you're mapping the state to a policy. How do you, that K times X, that's your policy. See? Okay. RL, reinforcement learning, seeks to learn a policy. Remember the learn. We'll see that. Learn a policy that maximizes the agent's reward in a long run. So that's the goal. The goal is to maximize the reward. Remember, I told you the example in a classroom, a student can maximize it. But in this case, the student may not learn basically the material. He learns how to beat the professor. Okay, so and it's important because in a very general formulation of the AI problem, and is objective with autonomy, no supervision. There is no supervision. That's why it is basically a form of unsupervised learning. But there is some supervision. Basically, the supervision is the reward. The reward always you want to maximize it. In some computer science guys, they minimize it. We minimize it. Control. Sorry. We minimize it because in a control, if you are using, you want to minimize the control policy or minimize the error. For computer science, they want to maximize it. So let's say you are investing in stocks, stock market. So what is your goal? To get maximum return, money back, right? So that's maximum problem. So most problems are either maximum, but for control problems we try to minimize it. It's the same. Minus max becomes minimum. So that's basically what a very quick stuff here, okay? So reward is a measure of desirability, like pleasure and pain. Remember, you get the reward. Let's say you are a student, you are studying 4 years, you do grades well, 4 years you're really slogging, and then at the end you get a good job, right, based on your GPA or stuff like that. But really what companies want to know is whether you learned the material. Even I didn't have that. When I was an undergraduate student, I was only smart on beating the professor in terms of what sort of questions he's asking, how to answer them, right? But the question was that the real learning happened to me seriously when I was doing a PhD. And I was taking that exam. That was not easy. Yeah. And then when I was doing my PhD work, it's not easy because your advisor will tell you scribble on something on a piece of paper. It takes me about 1 semester, 4.5 months to understand what was scribbling. So those are basically you learn. That's why I asked you, think about what is learning and adaptation. A lot of us do adapt but not learn. That's a big problem. So, but our actions are not guided by immediate reward. Typically when you are in reinforcement learning, when you are dealing with it, you are not looking at just that one exam. Remember, you want to get A grade. So when you want to get an A grade, it's not enough many times to ace an exam. If there are 3 or 4 exams, just acing one of the exams, it will not translate into getting A grade. So you have to have a long-term plan. You have to do well on all the exams, all the homeworks in order to get ultimately a good grade. That's the same thing, okay? And you need to also predict what will happen in the future of what. That's what we do in a reinforcement learning. So sometimes we do non-pleasurable things in order to get pleasure. That's what I say. You work hard, you slog during your, your parents think you're really working hard, right? But the guys will be going to movies and stuff like that, and that also I have done. But what will happen, naturally it will affect your grade at some point in time. So it's not like you're studying only before the exams. So we eschew pleasure if it stores up pains for us later, right? So sometimes you basically overlook the pleasure if it gives you a better life in the future, okay? So in reinforcement learning, the mapping from states to predictions of later reward is called value function. So that is what you want to learn. So what do I do now so that I can do better in future in my life? I'll give you an example. I have a roommate from when I was a student, IIT Kharagpur. You know what he told me when I was learning machine learning? He said, Jack, don't do it. And he's correct in a way at that time. Because AI, people used to call AI had a lot of ups and downs. I don't know, you might have not seen it. So I have seen ups and downs. So when people used to say 80 is AI, means people say that's a really shitty field. People are cheating. Even now I can tell you right now. So a lot of guys who talk about in Google is not really AI stuff. That's very focused on some specific application. This is what a Princeton professor posted on my LinkedIn. Look at it. In order to control a process, you don't really need tons and tons of data. I can do it. If I have time, I'll play some videos. You can do it with the 8086 processor, with a 8-bit processor with a very limited memory. So a lot of things we do in a real AI is not like having a data storage, cloud platforms. You don't need all that stuff. So this is what a Princeton professor recently posted. All these people in Google and all, why do they talk about big data and stuff? Normally we don't do that. So there's a different meaning to people, okay? So I think it's important. The most important is you got to learn, and that mapping that you learn from states to prediction of future reward is called value function. So if you really learn that value function, then you basically can do any action so that gives you the best performance in the future, okay? They are all efficient methods for solving multi-step problems. Learn value functions at an intermediate step. So this is important, and you guys will come back to me and teach me what's the difference between learning and adaptation. Remember, I told you that. That's a homework problem. So traditional adaptive control. This is very important now, okay? I only have 20 minutes. Some of you told me that you guys studied or you're working on adaptive control. Okay, traditional adaptive control is not optimal. Now, what is optimality? Optimality means you're coming up with a value function that either maximizes the reward, or in control terminology, that minimizes that value function. So let's say you're driving a car, or if I am a student in my undergraduate, my goal is what? How can I have fewer number of hours I can work and I still get a 90% grade? That's what I used to do. The least possible amount of number of hours I can study and I still get a A grade. But that's not learning. Remember, I told you that. That's a big miss. Yeah. That's what all of us do, unfortunately. That's easy. So that's not what it is here. So adaptive control, if you look at adaptive control, I already told you. In adaptive control, you A and B matrices, and the goal was you don't know A and B, and you are finding a rule to estimate. We call that as an adaptation, and then we control it. So traditional adaptive control is not optimal. And traditional optimal control, if you have taken a course, is not adaptive. But in the network control system, you need both. Because AZK and BZK is not known precisely. And why is it not known precisely? Because of we call network imperfections. Because those network quantities, they are random variables, like the delays and packet losses. They follow certain distribution. They don't, and even the distribution, we assume it's known. Many times may not know. So basically that makes the dynamics unknown. Okay? So traditional adaptive control is not optimal. So you have a parameter estimation, you estimate the parameters, and then you control it in adaptive control. But you don't minimize something in the process. Okay, so let's look at so you have a nonlinear system. Let me look at linear system first. You guys don't, okay. So this x dot equal to ax plus bu. So this is a very simple linear system. Now, anybody has taken linear systems background? Everybody has taken a course on linear systems? State variables? Yeah, everybody has taken, I'm hearing nodding, right? So you guys know what is controllability, observability and all? Okay, I think you should know that, right? So you have a x dot equal to ax plus bu. This is a continuous time system. A and B are precisely known. So I'm defining a value function, a cost function here. Okay, this cost function has two terms. This is called cost to go. This is called final cost. So cost to go is basically from one step to the other. I'm looking at the cost. So let's say your train goes from how do you pronounce this name? This city's name, Jasruguda. What do you call this? Huh? Jashguda. How do you say that? Okay. So that is the name, right? Let's say you go to the place you are going to, probably where I flew from. This is Rourkela. So you're flying to that place, and then you're coming to. So you have multiple smaller towns or villages. So if I want to drive a car and I want to minimize the fuel and the time, so that's basically what this term is here. This R. So it's a quadratic cost function. So I have x times qx plus u times ru. U is my fuel. X is the path that I'm following. So I want to minimize the path. I also want to minimize the fuel cost. So this term is called cost to go. And this has integral t to tf. So from that Jasraguda airport, I drive from my car from that place to the next village. the fuel consumed, right? I want to minimize it from that point to next one. So that's the integral term, T to TF. TF is the final time. Okay, so this is the cost to go, and this is the final terminal cost. The terminal cost is basically where I will be in the Rourkela. Okay, so this equation is called recursive equation. V of x comma t is the cost to go from that one place to the other, plus the cost to go from that place to Rourkela. Okay, so that is a recursive equation. Okay, and that recursive equation is usually expressed as an integral term or summation in discrete time. So this equation is called a Bellman equation in continuous time. So you take that v of x of t to the right hand side. V is the value function, and that's equal to 0. In ideally optimality, this left hand side will become 0. Now remember, in high school you treat this as a function. How do we determine what is minima or maxima, guys? How did we determine that? In high school we studied this. We take you take the differentiation and you equate to 0 and you solve that. Then once you solve it, that's the minima or some variable we call stationary point. Then how do you know that's minima or maxima? Second derivative. We are going to use the same thing. So there's nothing I teach that's hard. Let me tell you this. This is what we call calculus of variations. Newton, Leibniz, they were doing that. You know, Newton was doing some other problem. Leibniz was doing planets. He was looking at the distance to find. So they were using, that's called calculus of variations. Okay. The other way to do it is called Bellman. That's why it's called Bellman equation. Bellman was 1950s. So calculus of variations are very laborious, very complex if you have multiple variables. So Bellman came out and found out a way to do it, a recursive way, and you can do it in the computer. So it's called Bellman equation. It's called dynamic programming. Okay, all the planes, everything uses dynamic programming. Even your email that you send, that protocol, it's called Bellman-Ford algorithm. It's called Bellman-Ford. Richard Bellman is a engineer, is a mathematician. He developed this thing called Bellman equation, and it's a recursive equation. You see this equation? This is recursive. This is the cost to go. So from a city in between to final destination. So this basically is a recursive equation. And the recursive equation, you're trying to solve it. On the left hand side, if it becomes 0, that's optimal. But in most cases, we make it to a small error value, a bound, saying that. So that means that if I can reach close to Rourkela, I'm happy. You see? And so that's the main idea behind it, okay? So this is what we call Bellman equation. But the goal is the same. I'm going to show you in a second. So let's say that you define the value function as this is quadratic, x transpose s times x. This s is unknown, typically. Now what you do, just like you guys understand, so what do? I define what we call Hamiltonian. Hamiltonian is a way to solve the calculus of variation. So I equate, instead of equating to 0, I call this as Hamiltonian. So I define a Hamiltonian where v equal to x transpose sx. So what do? I basically took the derivative, that's like what you guys did, and I got this expression, okay? And then you see that partial h over partial u equal to 0, that's the principle of optimality. So if something has to be optimal, I take the Hamiltonian with respect to u equal to 0. If I do that, and I solve this h equal to, take the partial with respect to u, and if I equal to 0, I end up in getting some expression here. That expression becomes optimal value. Okay? Now, let me ask you, how do I get those x dot here? How do I get that x dots? So the reason you got x dot is because you have to use the dynamics here. Remember that? So v is defined as x transpose sx. So v minus delta v, which is the first difference, that's v dot. So when you get a V dot, right, V in a Euler's integration, remember that, what is x dot in Euler's integration? X dot is x of t plus capital T, which is the sampling interval, minus of V of t over capital T. Euler's approximation, that's the derivative in discrete time. So basically what you did is you took the V dot. V dot is basically you use the chain rule or product rule. So when you take the product rule, you get x dot transpose s times x plus x transpose times s dot plus x plus x transpose s times x dot. That's what I got here. You see those three terms? And this x transpose qx plus u transpose ru comes out from here. So this v minus v, this term gives you that term, those three terms, and these two terms basically coming out from this integral t plus t plus t. So basically what you got is this equation comes out from using this, and then you take partial h over partial u. When you take partial h over partial u, what will happen here? Remember, you got to substitute wherever there's an x dot, ax plus bu. Okay? If you substitute that, when I take partial h over partial u, what do I get? So I get this equation, there's an r coming in, and there should be x dot will have ax plus bu, right? There's a bu. So there will be here, so I get r's, and then there will be some other term, and then equate to 0, because that's what I showed here, and then I get u equal to minus r inverse b transpose this. Now you take that equation, plug it back into Hamiltonian, I get that equation. This is called Riccati equation. Now how many of you take an optimal control class? Have you heard of Riccati equation? That's the Riccati equation. Now look at the Riccati equation. So in order for me to come up with an optimal control policy, I have to solve this equation. Why do I need that to solve this equation? Because I need an S. S is the solution of the Riccati equation. Now, look at the Riccati equation. In order to solve the Riccati equation, what do I need to know, guys? Can somebody tell me? Huh? A and B matrices. Okay? I'll also ask you more. So since you took the optimal control, how do I solve the Riccati equation? How do I solve the... So what do you guys do in your course? Did you solve the Riccati equation? No? Oh, that's bad. Oh, that's bad. Yeah, that's the problem Indian teaching. That's bad. So you're going to solve that in, some of the, there is a code that I gave you. You try it out. We won't have time to go through, but yeah, I think that's the problem. What happens when MATLAB has problems? There were times MATLAB has problems. What will happen? Let's say somebody said he's designing a controller for aircraft, aerospace systems, right? And you use MATLAB, and MATLAB had problems. What will happen? What will happen? Huh? Yeah. How do you know that the result that MATLAB gives you is correct or not? Huh? Yeah. Well, MATLAB updates every time. They had problems. Every time they have problems. So don't assume that MATLAB is the... And they fix it. A lot of errors there. Many of us report. Yeah. So in a 2-minute thing, I'll show you. So if you don't have A and B, you cannot solve the Riccati equation. Okay, number one. Number two, this Riccati equation is a quadratic equation. There are boundary conditions, just like in partial differential equations. There is a boundary condition, which is initial condition. There is a boundary condition is the final condition, okay? And you have to solve that. Traditionally, in order to solve this, we have to use numerical methods. Remember, we do undergraduate numerical methods. Have you heard of that, right? Yeah, you see? This is why you can't forget mathematics. You have to solve it numerical methods. There's no closed form solution. Now, if A and B is constant and this is a infinite horizon. We call that problem as infinite horizon. Did they teach you in their optimal control? There are two types of problems. One is finite horizon, and the other one is infinite horizon. Infinite horizon is like temperature control. You set a temperature for a room, you leave it. Right? Process control, you maintain a certain temperature. But there are a lot of tasks that we do, like driving a car, you do a lot of maneuvers. Those are finite time. Those are finite horizon. In a finite horizon, it becomes even more challenging. That's basically becomes, And so there is no closed form solution for Riccati equation. Now remember, the Riccati equation, which is what I showed you here, and it requires A and B. Let's say, even if I don't have A and B, can I solve that equation? You can't solve that equation. So for network control systems, if I don't have AZK, BZK, I'm not able to solve it. That was the problem. You see? So in the course, you will see that how to do this. And so if you do this, you see that this becomes some K star times X. K star is Ackermann's gain. The only difference is this becomes optimal. So what do we do in optimal control? We solve every time. You find the S, and once you find the S, then you multiply this and you come up with the K. So for finite horizon, that K varies with respect to time. K constantly changes with respect to time because S is changing with respect to time. For infinite horizon, S becomes a constant or a steady state, and when it becomes steady state S, then K becomes, you can compute K, K becomes a constant. That's called suboptimal control. Okay? So either way, you have to solve that equation, you have to solve it numerically. Okay, that's a linear. So we're going to do that, and it has to be solved backward in time. Remember that. Now what is that backward in time? Again, because you guys never showed, people have not taught you. So that means that you have a final boundary condition, you start from the final boundary condition and you're going backwards. That's how all optimal problems are solved. The problem with, because of that, they were having tough time implementing in real time until about, I would say about a decade ago. We were doing this. So whatever you are learning, we are going to do forward in time. So you're computing the controller gains optimal in a forward in time. That's one thing that machine learning would do. Okay, the second, what you're going to cover is, we don't need A and B. That's the beauty of it. Remember that. That's why I told you earlier, you change the system, the controller would work. Only you have to adjust the learning rates and stuff like that. Yeah. So optimal control, that's the problem. If you don't have A and B, you can't even solve it, even though you're wanting to go backwards. So in traditionally NASA and stuff, any aerospace application you want to do optimality. Why? No, that's not the reason. Even if I know A and B. Why in aerospace applications you always want optimal control? You have to optimize the fuel because you are carrying the fuel along with you. It's like a weight. So they do all these studies offline and use those gains. But what is the problem with that? Things change. Environmental disturbances, so many things change. So they didn't know how to solve it, whereas the dynamic programming method and coupled with reinforcement learning, you can actually do forward in time. So you can do in real time. That was one of the major things that you're going to study. You see? So, any questions there? Any questions? So, this Riccati equation, if I apply this to nonlinear systems, so here is a nonlinear system. X dot equal to some nonlinear term f of x plus g of x times u. This is called an affine system, okay? And you do the same thing. You do the same thing for a nonlinear system, okay? So, if I do the same thing, then I get a Hamiltonian. I'm doing that the same thing with a Hamiltonian. Remember that, I'm not going through. This is how I go through. There's no time. Okay, you're going to see that. So the idea is the same. You define a Hamiltonian, you do this, the same thing as recursive equation. You take the derivative of h equal with respect to u equal to 0. you get that U star becomes like this. This is the optimal policy. V star is the optimal value function. You take that, plug it back in Hamiltonian, you get called HJB equation. HJB stands for Hamilton, Jacobi, Bellman equation. So that equation is for nonlinear systems. Riccati equation is for linear systems. So Riccati equation becomes a HJB equation for nonlinear systems. Now the problem is the same thing as Riccati. Even if I know F and G, look at that. This HJB equation needs F and G. F and Q, remember that? G here. So you can solve it. Even if I am given that, there's no closed form solution for that equation. There's no closed form solution even now. Only under some conditions mathematicians came up with a closed form solution, but not generic situation. So there's no closed form solution, the same problem. You can solve it from backward in time, people were not able to implement it, all that stuff. So we will use some approximation based methods. That's where we're going to use neural networks, you see. So we're going to approximate the V function, and when we're going to approximate this, and then we're going to solve it in real time, and then we're going to use it as part of the control policy. And as time progresses, we are going to go forward in time. We're going to start t equal to t naught, and we're going to go like that. And as we'll know more and more due to interactions, we get better, we learn better, and we are able to assess F and G or A and B, and then we are going to come up with a policy that ultimately becomes optimal. So when I show you some results, we are going to compare when A and B is known and A and B unknown, and we're going to map and compare it. One is going backward in time, other one is going forward in time. You'll see that very little changes. So last 15 years, many of us, spend this time. It's a big deal right now. NASA, a lot of applications, because so far nobody is able to do this solution forward in time. This is a big deal. That's why I said you need to appreciate, you can only appreciate, how you can solve this or what are the challenges. Okay? All right, this is my 5-minute stuff. The same thing you can do in discrete time when the system is in discrete. All right, you will have the discrete time Hamiltonian. This is a forward difference operator. You end up in getting an optimal policy. The same thing you need the dynamics. This is the, this may be a little easier for you to understand. So here is a discrete time system. Look at that. Here is my cos function. I equal to k to infinity. I can write this equation as a recursive v of x of k equal to k to k plus 1. I get this plus this term plus v of x of k plus 1. V of x of k plus 1 goes from k plus 1 to all the way to infinity. So that is a recursive equation. You can see that. So this, you see that v of x of k, k to infinity equal to k plus 1 plus k plus 1 to infinity. That's what I mean by saying that recursive equation. That's called Bellman equation. So airline scheduling, they use dynamic programming through Bellman equation. So dynamic programming is one way to solve the efficiently optimal control problems. Calculus of variations were the traditional way of solving the optimal control problems. Okay? So you can see that the same idea that we did in high school math, you define a Hamiltonian, you define a value function, x transpose some p is not known times x. Then you write the Hamiltonian. It's very easy. See, k to k plus 1 plus k plus 1 to infinity minus v of x of k. You see that how it comes out now. Then you take partial h over partial u equal to 0. You get this. In discrete time, you get this equation. Okay? So in your course in reinforcement learning, we are using reinforcement learning to learn the A and B for a linear system. And we use the Bellman principle, dynamic programming. So this is how the reinforcement learning comes in. And once you do that, you are learning that, then we use the adaptation, just like in adaptive control, to come up with the control, control policy is through optimality. A and B is coming from adaptiveness. You merge these two, you get what we call optimal adaptive control. You have the adaptive control that's optimal, or optimal control that has the adaptive component. Remember that? All right. So I think ARE stands for algebraic Riccati equation when the infinite horizon. Okay. So that's what the optimal adaptive control is. In 5 minutes, I'm going to wrap it up. So the problem is, look at the math. You need the math. So I don't know P in order to solve that equation. So I need to pull the P outside this. Can I pull it out? So if I have a X transpose PX, X is a vector, P is a matrix, X is a vector. So I need to pull the P outside that product. So there is fortunately there's a mathematician who came up with something called Kronecker product. So you can pull it out and make this as a vector. So that means that each row or each column you can stack it. Okay, you make it as a huge vector, a matrix. Okay, and then you see that xk, Kronecker xk. So then you can write this as a vector, and this is another vector, and either this becomes some basis function. So this is how basically you write it using a learning system or basically a neural network. If it's a nonlinear, you do the same thing and you can write it with the error in here. So there are some mathematical tools you need to know. That's why I said you got to learn the mathematics, otherwise you can't solve it. So I told you easy, you can add the reinforcement learning along with it, but really how do you do that? Those are the details. The devil is in the details. You have to use a Kronecker product, okay? So I won't explain that. I'm assuming you can search it. Then we can use what they call iteration methods, okay? They iterated and they came up with the P matrix, and they call policy and value iterations. There are ways to solve the HAB equation. And here is what we call actor critique implementation. So this is coming from psychology. So you have a critique. Critique minimizes the cost function, and the actor uses that information and generates a control policy. So some of you, if you look at papers, they talk about actor critique. How many of you heard of that actor critique policy? So where did you hear that? Policy. So why did you look for such papers? Oh, I see. So that's basically where. That's right. So actor critique is one neural network. Actor is another neural network. Critique basically approximates the cost function because we don't know. Remember, I just showed you that this is basically the value function, right? But there's no guarantee it will be like this. I don't know P, therefore I don't know this. And look at the control policy. Even if I know P, I need to know A and B. So as a consequence, I don't know U. So I need two neural networks, one to approximate U, the other one to approximate my value function. It's called actor and critique because it has two neural networks. Okay? And that's why it's called optimal adaptive control. So there are so many different methods. When there are some challenges with value iteration and policy iteration, which was published in 2012, you can see if you use in some of these methods, you really need infinite number of iterations or very large iterations. If you use very large iterations, it converges nicely. So iterations within a sampling interval. That means you're running all these optimal equations. Remember I showed you, you have to run it multiple times within the sampling interval. So if your processor doesn't have the computational power, you can't run them, it blows up. That's what is shown here. So we came up with, when we were doing with my PhD student, we came up with what we call time driven, and that's what all the software code that I gave you. There is some code on introduction to RL. You guys can try it out today. Run it. Actually, there is the main program in there. Do they have access to the code? Not yet. Okay, so you're going to tell them? Okay, I think you may want to tell them for 2 minutes. And you can run them so that you get familiar with these, whatever I'm covering right now. And before you come back tomorrow, because otherwise you will be completely not able to understand that, okay? So quickly, let me show you. Here is the linear system. What if I don't know A and B? So what we do is, we use what they call Q-learning. How many of you heard of Q-learning? So Q-learning is another way to do this for linear systems. So look at that, what I did. I took this equation, I am formulating it as a Q function, and this Q function writes V in terms of some adaptive control problem where H is unknown. So H is basically these set of issues here, H. So what do? I'm learning this H over time using my adaptive control background, okay? And by learning this, I take R inverse, this, taking inverse of that, multiplying by that, would give me my control, K. Because K is unknown. So I'm posing this problem as an adaptive control problem with an optimization there. So by doing this, I'm able to compute the Kalman gain R inverse B transpose S. I don't know S, but I'm learning over time, but I'm not learning S alone, I'm learning the whole K. And K is what? K is basically taking this term, this matrix, this term, R inverse, and multiplying by that term would give me R inverse B transpose S, and that gives me my K star. So this is how Q-learning is used to solve this optimal problem when A and B are not known. You see? When A and B are not known. So I rewrote mathematically, I wrote that equation, the Bellman equation, into a vector X and U transpose, and then in the middle I have a matrix. That matrix is given by this. So once I know the matrix, I can pose this problem as an adaptive control problem, and I can update, okay, just like in regular adaptive control, I'm learning the terms of this matrix in real time, and I am updating it. I know R, I know this term, I take the inverse of that, I multiply by that, fortunately gives me a K. And that's what I'm looking at. So once I get a K, I get U equal to minus K star times, and that K becomes optimal control gain, fortunately. Why? Because I started using this Bellman equation. And therefore, it ties with Bellman equation, which is for optimality, with the adaptive control that I learned as a student, and merge those two, it becomes a reinforcement learning problem. The same thing we do in nonlinear as well, okay? So the nonlinear, so this is the block diagram. So you take the batch reactor. Let me quickly go through this. Here is the batch, X dot equal to AX plus BU. You see that X, it's not showing up. The version problem. This is why I said sometimes the, so this is a batch, linearized batch reactor, A matrix and B matrix, okay? I am trying to run this batch reactor 0 to 10 seconds using Bellman optimal equation. So now you see that I compared this equation in two cases. Look at that. One is Riccati equation based traditional optimal design, the backward in time, okay? So you see that that is red, and blue is the one that we developed. Now why is batch reactor? Because, you know, I don't know how many of you know, probably you might know, you know, have you heard of this company called Procter & Gamble? So go back and look at it. There are a lot of things, many of these companies make a lot of products, right? And these products, many times you optimize it. It's a process control industry. Many times these are huge. It's a chemical. Many times you don't know the dynamics. That's another area that if you don't know the dynamics, you can't solve it. So here what we were doing is we are using the Q-learning to solve the optimal control problem. So A and B are not known, but I assumed I know that, and here is my Riccati based solution, which is a backward in time solution, and then I'm running this controller in real time, the optimal adaptive, and you see that how close it is. So it's an approximate solution, still does a good job, okay? So here is how you do it. You can there is a code we have given you. You can run them. I think he's going to explain to this. So in a nutshell, You can do this in discrete time. See that controller block diagram? You can do it in nonlinear systems. So here is adaptive. You have an identifier, you have an actor, and you have a critique, and you can actually use the mathematics I explained and nicely draw this block diagram with different colors. Of course, you do it after you publish it. You nicely make that block diagram. There's a meaning to it. This block diagram explains everything what without understanding how I derived. So here is a system dynamics. I'm measuring the state. So you see the identifier basically computes the F and G. I'm estimating the dynamics F and G. And once I get it, then I'm using that F and G in a critique network, which this is the update loss for the critique network. And then there are terminal constraint error. I define a Hamiltonian. This is called estimated Hamiltonian because you have a hat there. It estimated based on the actual values. I use this information to obtain my control policy, which is generated by the actor network, and that control policy is applied to the system. So over time, I show that the actual control policy you had converges to the optimal control policy U star. And that's what happened in that example I showed you. You see? So this uses, this is a nonlinear system. I can use Q-learning. I can, but we didn't use the Q-learning. So here we're using neural networks. We use the actor critique systems in there. Okay? So if you don't have reinforcement learning, guys, this is the quickest way. And you can take a two-link robot and you can show similar results. And you can get very good results. We have implemented a number of examples, over 500 real-time systems. You know, they work pretty good. Okay? So I think this is a reinforcement learning applied to control. I'm going to stop here, guys. As I said, see the robot example, and we have time. We can show. I can show you play the videos. And normally you can compare with stabilizing versus optimality, because why? Otherwise somebody will ask, why are you doing optimal control? So what is the difference between a stabilizing control and optimal control? What is the difference? Have you heard of stabilizing control? Probably you might have heard. What's the difference? What is the difference between a stabilizing? Have you heard of word stabilizing? I'm positive, right? A stabilizing control and optimal control. What is the difference? So I'll tell you something. If you are able to solve optimal control, you're also doing stabilizing control. It's even more than that, because you're also trying to do an optimal loop in there, right? You're trying to optimize it. In a stabilizing control, we don't do that, right? So optimal control is the best if you can do it. And remember, I told you the problem with optimal control is the backward in time solution. This is why hardly it was implemented in real time, but now I think you could do that with machine learning or reinforcement learning. That's the beauty of this class, that yeah, it goes forward in time. So stabilizing means you're only trying to make the system stable, right, with some performance index. There's no optimality. Whereas when you're talking about optimal control means you're able to make it stable. That means by default, you claim it's an optimal control means it is stable control. Otherwise, it makes no sense. And in addition, you're trying to find the minimum or maximum. Remember the loop that you're trying to optimize it, okay? All right, guys. So these are hardware results, and I don't have time here, but you know, I also compared with MPC and the proposed approach. Some of you said model predictive control. There's a lot of things. Model predictive control requires the dynamics. That's the requirement in a. Whereas the one that we have been going to talk about it, you don't need the dynamics A and B. Remember, I told you that. I went through this quickly. I provided these slides. I think Dr. Behra is going to, you already have shared them? Okay, so he's going to share those slides. Okay, unfortunately, we don't have time because this is not network control system. I'm giving you background on reinforcement learning. And this is a very quick 1 hour background. It took me probably about 10 years or more. So That's what the time we have, because we are going to spend all these concepts, we're going to apply to the, and we're going to look at these, you'll see that Q learning keep coming in, and so I would rather have you go through these slides, and there is a couple of code, intro to RL, there's MATLAB code, you can run them, blindly you can run them, it should run, okay? So he'll also explain to you, and do that before you come to them tomorrow morning, and review these slides, the Q learning and stuff, okay? Because we're only going to do 20 lectures, 20 hours. I know we went beyond the 2 hour today. Supposed to stop at 1 o'clock, otherwise I won't get my lunch. Yeah, okay, all right guys. I'm going to stop here, okay? Thank you for your time.